All right, I'm going to do this example. Um, we have a radar signal that leaves Earth. It bounces off a comet and then returns to Earth, and the round trip time takes 500 seconds. Okay, so our first question is how far away is it? We can use the equation, the distance um, equals the speed of light, because of course radar travels at the speed of light. Um, the speed of light times the round the well half the round trip time, right? Because we'll talk about that in just a second. If the angular size of the comet, as observed from the Earth, is 0.07 arc minutes and 0.53 arc seconds. Okay, so that's an angle, right, in arc minutes and arc seconds. All right, so we're going to need to convert that. You'll see what I mean in just a little bit. We'll convert that amount to degrees. We'll do that together. And then once we do that, we can figure out the actual size of the comet. All right, we're going to use the speed of light is 3 times 10 to the fifth kilometers per second. And the reason that we're going to do that, of course, is it'll give us an answer in kilometers, the distance, and also the diameter of the comet. All right, so let me get this set up. Sometimes it's helpful to draw a picture. This is the Earth, of course, this little circle right here. This is the Earth right here, and then here's our comet up here in the top left hand corner. And so we're sending a signal, like it's a radar signal, right? So this is supposed to represent radar. So the radar signal hits the comet, right? So it keeps going, hits the comet, and then bounces back. All right. So this is the signal returning towards the Earth. This is the signal going towards the comet. And so really we want to know is this distance right here. Right, so that's the distance that we're looking for. And of course, what we're going to use is this equation. The distance is equal to the speed of light in kilometers per second times. Now, it's not the round trip time; it's half of that. All right, so this is the I'll call it RT, the round trip time. Um, that's T sub RT divided by 2. Why divided by 2? Because it takes the time it takes to get to the comet and then the time it takes to come back. We're only that would give us twice the distance, and we don't want twice the distance. We want to know what the distance to the comet is. All right, so that's all right. Let's solve this. All right, so I just set up the problem. This is the speed of light, it's 3 times 10 to the fifth, times the round trip time divided by 2. All right, so let's go ahead and do that. So of course it's going to be 500 divided by 2. And we already know what that is, but then we multiply that times the speed of light, so that's 3. Remember, you got to know how to enter scientific notation on your calculator. For this one, you just hit the EXP button. For sorry, that's like a Casio. For Texas Instrument, there's a shift or a second, and then there's it's not on this one, but it's an EE button. Then so that'll tell you that. Anyhow, so it's 3 times 10 to the fifth. All right, times the 250, and so this gives us that's the distance to this particular comet with this example. All right. So let's write that in scientific notation. So it would be 7.5, right? 7.5 times 10 to the, that's supposed to be a 10, sorry, times 10 to the seventh, right? And that's kilometers. All right, very nice. And of course, you could write it as 7.5 E. Just like if you did this problem on Blackboard, that would be 7.5 E7. That's perfectly fine to write it like that. All right. So here, let's look at the calculator one more time. All right. So how did I get this? The 0, it's implied. It's right here. So I move it over to the left 3, then 3 more, and then 1 more. So that's why it's times 10 to the seventh. and of course it's kilometers. All right, so that solves the first part of our problem. All right, I'm going to set up the equation for the diameter. Well, yeah, let me do that. I'll set up the equation for the. Here, might as well just do it while I'm talking. Okay, so the equation works up like this: the diameter of something, and this comes from geometry, right? The diameter of something, and I'll use diameter. Um, DIAM for diameter, is equal to pi divided by 180, right? Pi divided by 180 degrees. So it's degrees, by the way. And that's times the distance to the object. D is going to stand for the distance, right? And then times what I'm calling alpha, which is the angular size of the object. All right. So that equation, it's in your textbook. It's in the first chapter in your textbook. If you look towards the end of chapter 1. At any rate, the important thing is that whatever the distance, if you know the distance to the object, which notice we just calculated the distance to this comet as 7.5 times 10 to the 7th kilometers, whatever the distance is, the diameter of the comet is going to be in the same units, right? Same units. Same. All right. But alpha has to be in degrees. All right. So really that's we already have what the distance is. It's right there. So all we have to do is convert the angular size. That's what alpha is. The angular size of it into degrees. All right. So here, let's. I'll write that up. So don't forget. I'll rewrite this equation in just a moment. Okay. So what we're going to do is we're going to convert. So in the problem, they gave us this angle. All right. It's kind of a strange way of representing an angle, but in astronomy, we often will talk about arc minutes and arc seconds. Remember, 1 degree is 60 arc minutes, right? So 0.7 arc minutes, 0.07 arc minutes in this particular situation, and 0.53 arc seconds, that's a really small angle in the sky, right? Because 1 degree is 60 arc seconds, and then 1 degree is 60 arc minutes, and then 1 arc minute is 60 arc seconds, right? That's so the 1 hash mark means arc minutes, 2 hash marks means arc seconds. Okay, please get used to that. We use that all the time in astronomy. All right. So, or you could write, so you could also write, that 1 degree is 60. So sometimes it's written like this, arc minutes. But see, it takes a longer to write that, right? And of course, 1 arc minute is 60. And so you often will write it like this, arc seconds. Right. But again, that takes longer to write arc seconds. And all right, anyhow. So how do we convert this? And remember, this is one angle, right? So it's kind of like, it's not exactly equivalent to this, but it's kind of like this is the decimal part of this, all right? Kind of, all right? So we're gonna convert them to degrees, and then, use that in that equation that I just showed you a moment ago. All right, so let's set this up. All right, so remember what we're doing here is converting the angular size of the comet. So this, you look from Earth, and it's an extremely small comet, right? The angular size of it. This idea of angular size, the analogy I always use is, like imagine a chair, right? Like there's a certain, the back of the chair has a certain diameter, like the size of the back of the chair. But if you were to move the chair further and further away, the angular size gets smaller and smaller, right? And so that's the first equation that I wrote, that's really the description of that. And so anyhow, this comet is 0.07 arc minutes and 0.53 arc seconds. All right, so we use these conversions. The fact that one arc minute is that's supposed to be here. That's supposed to be a here. Let me use the that's a is 1 degree is 60. That's supposed to be a zero. Sorry, I didn't make one degree is 60 arc um, minutes, right? And so the arc minutes are canceling. All right, that's the idea. And then plus 0.53 arc seconds. Of course, in one arc minute, there's 60 arc seconds, so the arc seconds cancel. And then in one arc minute, remember, we're changing it to degrees, right? In one arc minute, there are 60 arc seconds, all right? And so you take this point, 0.53 and divided by 60, divided by 60 again. That's going to be a really small number. And then you add that to 0.07 divided by 60. And when I did this is what you get if you round it. Let me just show you that real quick using the calculator. Well, I already did it, but see that's you can see it's 0.07 divided by 60 plus 0.53 divided by 60 squared, right? And so this is what you get, unrounded, but I rounded it, where that first 80 is, right? So notice there's an 8 after it, and so I rounded that. So it's 0.0131, sorry, 0.001313. Let's see, did I get that right? 0.001313, and since and a not 9, all right. And now that's in degrees. Now we're ready to solve the problem. Okay, so we're going to use that number right there to do this. All right, and putting all of this together, this is our original equation: pi over 180 degrees. That's supposed to be a little degree sign right there. Times the distance. Remember, we've already calculated the distance: 7.5 times 10 to the 7th kilometers times alpha, but alpha has to be in degrees because basically this degree right here and this degree right here have to cancel. And so this was our alpha in degrees. So all we have to do is multiply all that together. All right, so let's see. I have my calculator. Here it is. All right, so I've already got the degrees in there. So we're going to multiply that times 7.5 times 10 to the 7th, and then times pi. Let's see, where's my pi button? Do I have a pi button? Where is it? All right, times pi, which is right here. I didn't see that. And then times I messed up. So it's got to be divided by 180. All right, I'm just going to say times 1, right, because that didn't change anything, and then divided by 180. Right, divided by 180. All right, so here, let me redo this just to make things simple. So it's pi times 7.5 times 10 to the 7th times this number here, which is 0.00131339. That's how we rounded it, and then you divide by 180. All right. And so that turns out to be, we're going to round it one place past the decimal. How's that? So it turns out that the actual size of this comet in kilometers would be 1,000. Oh, I didn't mean to make that go away. 1,719.9. So 719.9. So 719.9 kilometers. That's the actual size of the comet. Okay, so it looks really small that at that angle because it's this far away. Right, if it was closer, it would be bigger. course. That's what this equation does for us.